Hello there, welcome to the Learning Everything We Can Learn from VisionOS Documentation series. This is our 24th video. We're going to analyze the performance of your VisionOS app. Use the RealityKit Trace template in Instruments to evaluate and improve the performance of your VisionOS app. To maintain the sense of immersion on Apple Vision Pro, the system attempts to provide this device displays with up-to-date imagery at the constant rate and respond to interactions with minimal latency. Any visual choppiness or delay in responsiveness interferes with the spatial experience. Higher power consumption over extended periods of time or extreme power consumption over short periods of time can trigger thermal mitigations that also impact the quality of the experience. It's important to minimize your app use of the system resources to ensure your app performs well on the platform. Many of the same best practices and optimization procedures you use to develop for other Apple platforms apply when developing for VisionOS as well. For more information about optimizing your app on other platforms, see Improving Your App Performance. To get useful information specifically to rendering bottlenecks, high system power use, and other issues that affect the responsiveness of your VisionOS app, profile your app with the RealityKit Trace template in Instruments. This template helps you identify complex content or content with frequent updates that cause the renderer server to miss deadlines and drop frames. Content and tasks that result in high system power use, long-running tasks on the main thread that interferes with efficient processing of input events, tasks running on other threads that don't compete in time to sync back to the main thread for view hierarchy updates. You can profile using a real device or simulator, but to get the most accurate and actionable information, use a real device. Software and hardware differences between a similar on a map on your Mac and a real device prevents you from relying on the timing information. Simulated devices are useful for quick iterations and improving performance aspects that aren't based on time. Open a new trace document. To create a new trace document, select your app schema and a VisionOS run destination from the Xcode project window. Choose Product Profile. Choose RealityKit Trace Template. Select the Choose button. Alternatively, launch Instruments and choose a target app from the template selection dialog. The RealityKit Trace template includes the following instruments: RealityKit Frames captures frames, rendered times, and lifespans for frames the VisionOS renderer server generates. This instrument indicates when frames miss rendering deadlines and provides average CPU and GPU render rates. RealityKit Metrics captures comprehensive timing information from the entire renderer pipeline, including rendering, committing, animations, physics, and spatial systems. This instrument identifies potential bottlenecks in your app process or in the renderer server as a result of your app's content and indicates areas of moderate and high system power usage that require optimization. Run loops captures and display run loop the execution details. Time profiler profiles running threads on all cores at regular intervals for all processes. Hangs captures and displays periods of time when the main thread is unresponsive. Metal application records metal app events. Consider adding other instruments to trace you for specific investigations. For example, you can use the thermal state instrument to record device thermal states to check if thermal pressures are throttling performance. Profile your workflow. Click the record button at the top left of the window to start capturing profile data. Perform the actions in your app that you want to investigate. When you complete the actions, click the record button again to stop recording. To investigate performance issues and analyze system power impacts, profile your app in isolation to understand your app's impact on system performance and ensure you get the most actionable information. For apps that run alongside other applications, profile your app again with those apps running to understand how people experience your app in conjunction with other apps. Okay, here we have our Hello World app open. We have our schema set to world. and our simulator set to Apple Vision Pro. Next, we're going to hit the product button, hit the profile button. Once you hit this button, we'll run the Hello World app. And then we're going to use a particular template called RealityKit Trace. Choose this particular trace. Once we do that, we will have this instruments panel, that template created. Here, we can record what is happening on our app. So we are recording right now once we hit that red button. Now let's make something happen on our Hello World app. Let's open the solar system, view outer space. Okay, and we are now in space. That was pretty quick. And we see the Earth and satellites, the moon, and the sun. All right, let's go back. Now, once we stop the recording, this is 30 seconds, we have our it's analyzing and collecting our data, recording the data for us. Once it's done with this process, we will have some data to view. Now we have our data. We can inspect this data, the RealityKit frames, to, again, look at dropped frames, average CPU usage, and GPU usage. Next, we have RealityKit metrics. This tells you about all the bottlenecks. These are points at which we can probably work to optimize our code to improve the thermal performance. Next is run loop. The run loop displays the number of which thread your processes are running on. In this particular case, we're running on the main thread. We have the time profiler. This tells us which thread we're running on in terms of CPU usage. The next instrument is hangs. This is where our app is creating a delay on the main thread, making it unresponsive. Metal application tells us about how metals app events. And if we want, we can add a heat check, thermal check, by hitting the plus button here to add a thermal state. By clicking this button, we'll add another instrument to our panel here to record. Here we have the thermal state. Let's run this app again and record and see how our thermal state is when we run this app. Here we go again. Hello world. And let's try the same processes again and check the thermal load. Look at the Earth, the sun, the moon, and exit. Let's stop it and collect that data again. Here we have collected the data again. In our thermal state, we have the unknown. I believe this is because we're using a simulator, so we don't have any thermal information about the device. However, what a funny thing is that we have many more hangs for some reason, and we're hanging much more often. Here's a time profiler where we're using 300% of our CPU for this thread. I wonder what's going on here. Well, we're going to find out more once we head in to our more documentation on how to read this information. Inspect frame rendering performance. To maintain a smooth visual experience, the system tries to render new frames for the Apple Vision Pro at 90 frames per second. The system renders at other frame rates depending on the content it displays and the current surroundings. Each frame has a deadline for the rendering based on the target frame rates. Not meeting these deadlines results in dropped frames. This creates a poor spatial experience overall. People tend to notice it in the visual performance of persona and share play experiences, video playback, and scrolling. The RealityKit Frames instrument displays the time spent rendering each frame in the frame section of the timeline. When you zoom out, you can identify areas with a high number of frame drops or with frames running close to the rendering deadline. The timeline uses green to identify frames that complete rendering before the deadline, orange for frames that complete rendering close to the deadline, and red for frames that don't complete rendering that the renderer drops. Drop frames contribute to a poor spatial experience. but frames that complete close to their rendering deadlines indicate performance problems too. Hold the Option key and drag to zoom into a frame or a group of frames to see their lifespans broken down into stages. This provides you with insights into which portion of the rendering pipeline to investigate further. This timeline also includes sections that visualize the average CPU frame time and average GPU frame time to indicate the type of processing that computes the frames. A region of the timeline without a frame block indicates a period of time without changes to the person's surroundings or app updates. The rendering server avoids computing new frames to send to the composer during these periods, which help us optimize power use. Right now we're back in Instruments. We're looking at frames. I see that there's some red here. Let's zoom in, let's see what's going on. Options and scroll into our frames. Here we're dropping our frames. This is frame 80,896.69. And it looks like it's a CPU. It's taking too long. And here is another one with the CPU and GPU taking too long. These frames are being dropped. We dropped a few frames and we're gonna pick it back up and have green frames. Looking at the average CPU and GPU time, orange is within the 15 milliseconds, green is within 10 milliseconds, and red is above 30 milliseconds. Anything above 30 milliseconds seems to be dropped. Here is our GPU usage. It is rather low, so this is why it's a CPU drop, not a GPU drop. We start dropping GPU once we hit this particular point where we're using too much GPU here. And then we're back down to a relatively low ms milliseconds for CPU and GPU before we stop dropping again for CPU of 43 milliseconds. Some of you might be wondering why we have 3 separate lines. I believe what's going on here is 30 frames per line, and these frames overlap to create a 90 frames per second that we monitor system power usage. When thermal levels rise to levels that trigger thermal mitigations in the system, performance degrades and negatively impacts the responsiveness of your app. Optimize for power to avoid these negative impacts. The timeline for RealityKit metrics instrument includes a system power impact section to identify areas of high power usage in your app. If the timeline displays green, the tool considers that your app impact on system power low enough to sustain. Regions that display orange or red indicates the system power usage could cause thermal levels to rise and trigger thermal mitigations. This decreases the availability of system resources, which can cause visual interruptions and responsiveness issues. If the render server can't maintain the target frame rate of 90 frames per second due to thermal pressure, it might reduce its frame rate in half. When this occurs, all frames in the frame track shows up as missing and their rendering deadline. Other factors can cause reduced frame rates, including the complexity and frequency of the content the system is processing. Use the thermal state instrument to determine if thermal conditions are causing the rate limiting, or if it's due to other factors. In our simulator, our metrics do not show power impact. All we get are these bottlenecks from our spatial systems or 3D render encodings. So we will need our device to look into this metric. Identify bottlenecks. The bottleneck section of the timeline for the RealityKit metrics instrument contains markers that indicate high overhead in your app or render server that contributes to dropped frames and high system power use. When you encounter either of these issues, check if the timeline identifies bottlenecks that you can address. Double-click on any of the markers to display more information in the detailed area at the bottom of the instrument window. Now let's first look at the detailed view. Let's click one of these bottlenecks. This is a GPU work stall. We have clicked the particular GPU work stall, and we see that here in the detail view, we found that particular frame. It's right here. It's the frame number 38. If the detailed area is hidden, choose a view, detail area, show detail area to reveal it. Now, the detail view and extended detail view is open. However, if you don't see it, here's what you can do. You can go to, particularly here In View, select Detail View to show Detail View. Here we are hiding the Detail View. Now we show it. The render server encounters bottlenecks in either the CPU or GPU. The instrument categorizes bottlenecks by their severity and type. To filter the bottlenecks listed in the detailed area to a particular time period, drag inside the timeline to select the region. Now, if there's a range of bottlenecks that you would like to take a look at, hit the right click it and select the particular range that you want to see. In this particular range, we have a bunch of high severities with a GPU work stall, it seems. You can clear it by hitting the view and clear inspection range. To see an outline view of the bottlenecks organized by severity and type, select Summary. RealityKit bottlenecks from the menu at the top left of the detailed area. Click the arrow button to the right of the severity type, or type in the outline view to show the list of bottlenecks in that category. To see an outline, hit this top left button here. Hit Summary of RealityKit bottlenecks. Here we have a summary. Here we can look into our GPU work stalls just for this particular type, severity and type. Now, you should see an arrow and you can click it. Now we have all of the items that have the type of GPU work stall and its severity is high. We can look at which one has the highest duration and look at that, how to resolve that issue. Another way to do this is to go back to our outline view. Then in our outline view, type into the filter GPU work stalls. And now we have all the GPU work stalls. When you select a specific bottleneck, the extended detail provides recommendations for you to address the bottleneck. Choose a view, show extended detail to view all the extended details if it's hidden. Extended detail view for extended details on how to fix the problem that you have. Explore the metrics that relate to bottlenecks. The trace provides additional information you can use to identify changes to make in your app to address these bottlenecks. Click the expansion arrow for the RealityKit metrics instrument timeline to reveal graphs specific to each major category of work. Use the metrics associated with these graphs to determine which RealityKit feature has the biggest impact on high CPU frame times in the app processes or in the renderer server. When interpreting these graphs, lower indicates better performance and power. The metrics represent values from all apps running, so profile with just your app running when trying to optimize for these metrics. The first is 3D render. Metrics related to the cost of 3D RealityKit rendering in the render server. This includes the number of draw calls, triangles, and vertices from all apps. Here we are looking at RealityKit metrics for 3D render. Here are 13 graphs. I believe these are the 13 graphs in total, the shadow triangles, vertices, total vertices, and much more. These are different types of calls our 3D renderer must work on. Next is core animation renderer. Metrics related to UI content rendering costs in the renderer server. This includes the total number of render passes, off-screen render passes, and translucent UI meshes from all the apps. The core animation renderer. Here are the render passes that we are making. We don't have any off-screen preparations, nor do we have any translucent UI meshes. Entity commits. Metrics related to the cost of entity commits in the app and the render server. This includes the number of RealityKit entities shared with the render server from all apps, as well as the number of updates received from all apps over certain intervals. Next, we have here the emit entity commits. Here's when our app receives updates every now and then. Here is the shared entity updates that we're getting from the rest of the app. RealityKit animations. Metrics related to the cost of RealityKit animations in the app and the render server. This includes the number of skeletal animations across all apps. For RealityKit animations, it looks like we have 0 skeletal animations. RealityKit Physics. Metrics related to the cost of RealityKit physics simulation, collisions, and hit testing in the app processor and render server. This includes the number of rigid bodies counts and colliders in use, as well as the number type of physics shapes that the UI and other 3D content uses across all apps. As for RealityKit Physics, it looks like we have some RealityKit Physics events going on here when we're touching the world, moving around, looking at the sun and the moon. Next is the spatial systems. Spatial systems. Metrics related to the cost of spatial algorithms in the render server. This includes the number of custom anchors across all apps. For spatial systems, we are measuring the custom anchors and the number of custom anchors that we are using. We have 29 custom anchors at almost all times. What are these anchors? They're anchoring the content to certain points in the spatial system. Tips. The graphs for some section combine several individual metrics. The head thing indicates that this by displaying a graph count. Click on the bottom of the timeline heading and drag down to display individual graphs for each metrics. For example, the 3D render timeline might display 13 graphs in the heading. Expanding the timeline exposes individual graphs for 3D mesh draw calls, 3D mesh triangles, 3D mesh vertices, and 10 additional metrics. The timeline for your app process helps summarize information from the instruments about your process, the work the render server completes for your process. Choose an option from the pop-up in the timeline header to show different graphs in the timeline. Run loop. Time each thread spends waiting or busy. Hangs. Time the main thread is unresponsive. Time profile. CPU usage and lifecycle status. RealityKit system timelines. Overhead attributes to RealityKit systems. When you select the timelines for your app processes, you can choose instrument summaries and profile data to display in the detail area from the pop-up button at its top left. To filter the information in the detail area by time, select periods of time in the timeline above. Next, we have the pop-up in the timeline header to show different time graphs in a single timeline. Here we have the timeline for your app processes. We have the ability to take a look at run loops, hangs, time profiles, and RealityKit systems. This is, again, the overhead for our RealityKit systems. Time profile is, again, for CPU usage and lifecycle status. And we have next the hangs for hangs when your main thread is unresponsive, and run loops to check when the thread is spending time waiting or busy. In the detail section, we can click this pop-up button here and take a look at the summaries regarding each item. Let's look at the hangs. Here's a summary of all the hangs for possible delays. Let's move on to hangs, the number of hangs that we have, and hang risk. We also have our run loops or time profile. Let's take a look at that. Here's our time profiles, samples, and life cycles. Let's detect delays on the main thread. Select hangs in your app process timeline to identify times in the trace that might have interaction delays. Use the RealityKit metric and time profiler summaries to better understand the work your app is doing. Choose the following options from the details area pop-up menu. Profile and samples. Show information from the time profiler instruments to determine what your app is doing during a hang. Summary. RealityKit some system CPU times show minimum, maximum, average times for the CPU spends on various RealityKit system operations. Optimize any 3D rendering updates, hit tests, and collisions work you find. For more information about addressing hangs in your app, see improving app responsiveness. Okay, let's look at a hang here. This hang happens around 10 to 11 seconds. Let's take a look at this hang. Let's see what's going on. So something that was suggested to us is to take a look at the time profiler in the detail menu. Take a look at the profile. Here in the profile, we take a look at what's going on. We see that the start takes up 4.69 seconds. So this is the main bottleneck that we have. That takes up most of our time. Let's take a look at the samples. The samples suggest that what's going on running in the background thread. Here's a backtrace, and we are looking at particular threads that are running. So in this particular case, we have the start sim, and this particular thing runs in the Swift UI and does a world init. And so what's going on is that we're creating a particular world. I believe that's when we clicked into our 3D spatial experience with the Earth, the Moon, and the Sun. Next, let's take a look at the RealityKit system CPU for minimum and maximum usage. Here we have a lot of 3D rendering usage here. This is what we should probably look at. The entity commit at this particular time is pretty ordinary. As you can see, it's the same as every other point. Let's take a look at custom reality systems and 3D rendering. So in 3D rendering, it looks pretty normal as well. Is there anything abnormal about this at all? Is it the physics? Or is it anything else? I believe it might be a memory collection issue. Looks like there's a lot of CPU usage here and nothing of much else. So it probably is taking the item from our hard drive and moving it into memory for our CPU to use. And that's the reason why we have this interrupt to our main thread. Manage audio overhead. Use the audio playback session of your process timeline to identify areas of high audio overhead. The system defaults to using spatial audio for your app when running on VisionOS. It processes information in real time about your position, surroundings, and the current location of the audio source to generate an immersive audio experience. If you include too many concurrent audio sources, that requires the system to adapt audio sources to their location within a large space. The increased demand on system resources can lead to delays in audio output. To reduce spatial audio work, limit the number of concurrently playing audio sources, the number of moving audio sources, the size of the soundstage. Consider creating a pool of audio players to limit the maximum number of players your app uses. Place players on stationary entities instead of moving entities when appropriate. Initialize several audio players at the same time causes a high overhead that affects other aspects of the system, such as rendering performance. Consider the other tasks that the system completes during these allocations and space them out over time. For more information, see creates a great playback experience. To inspect your audio playback in your instruments, go to Backboard and look down at the detailed view at the 10 graphs. You'll see audio playback. In our case, in Hello World, our audio playback is not taking up much headroom at all. It's only costing us 5 milliseconds than the max duration. So it's pretty good. Alright, we have come to the end of this article analyzing the performance of your VisionOS app. There was a lot to learn today, and a lot more to learn when we're performing performance enhancements on our VisionOS applications. Now we know what to look for and what to fix when we see it. Alright, hope you enjoyed the video, and we're going to head on to the 25th video next.